Hi, everyone. This is Kerim with SolarAcademy. Today, I have with me again Mike Burz of Enzinc and John Bonanno, who's a senior advisor to Enzinc, as well as a number of other clean tech startups. And recently, John, you and I were on a call and you were explaining the amazing facts about the battery, the storage landscape. And what do you call it? The lies?
Well, there's in energy storage, there are lies, damn lies, and marketing.
Damn lies, and marketing. Okay.
I think we should also start with acknowledging this very interesting moment around global energy dysfunction. And I have to say, I have a personal bit of PTSD around this issue because as a survivor of 9/11, the violence and the chauvinism and the centralization of energy was crystal clear that morning to me. And we're seeing this again, so sadly, 21 years later, or is it 20? Yeah, 21 years later, we're seeing natural gas manipulation allow an incredible aggression from one person against another person. And if we had defunded at high scale and velocity the fossil economy at the postscript of 9/11, those attacks, we would be so far ahead on defunding the violence now that this would not be possible for Russia to do this. And frankly, I have worries about other places in the world around energy manipulation. But in order to decarbonize at an extremely, extremely deep way, where you have massive amounts of solar, massive amounts of wind, I have a personal view that there's a requirement of modular, safe nuclear. But if we're going to do that, we have to decouple the intermittency of solar and wind resources and enable that clean electron to be stored and used when we need it. So to be dispatchable and to be the highest value. And so you then have to think, all right, well, how are we going to use this in our mobility, in our homes, in our businesses, in our industry? How do we use it in a network? It always requires superior energy storage, but energy storage systems, systems that you account for from the beginning of the mining process right through the end of life, and also must include what the application requires. Temperature control systems if they're required, armor if they're required, if someone's going to jostle it around or shoot something at it. Complex battery systems, because maybe this particular solution or another solution requires it to be treated like a very special little trinkety thing. And if you mistreat it in any way, bad things happen. So I think that very sadly, there's been a procession of marketing and communications around how lithium is going to solve everything. And that is utterly false. Entirely false, and frankly, very dangerous, not only because of the fires that are possible with lithium technologies and energy storage, but also because the supply chain from mining to processing is almost entirely controlled by one country.
China, yeah.
And it's China. And I'm not a sinophobe. In fact, I believe very strongly in partnerships, humanitarian partnerships, human-to-human partnerships. And so I'm not an anti-China person. I'm simply saying it's not good for humanity to have such a constriction on a key element.
I mean, this whole conversation is about distributed energy, distributed power. And if we want a healthier planet, we do want distributed power. And that applies to parts of the supply chain to be distributed as well. Yeah.
And what John is talking about, Kerim, is not just when we say distributed, we don't mean distributed in terms of geographically, but we also mean hierarchically within, a society. For this to work, right? It's not just one level that can have all the technology, right? Or all the chemistries. It has to go, deep and broad throughout the society.
Yeah, it's got to have
hopefully that's
access.
The premise of solar. I mean, right now we're approaching what 3-4 million homes in the US having solar, which is great. Still 3-4%, but not quite at 30% like Australia, but we're getting there. I think it's going to go there very, very fast.
But your point there is so valid, is that the access to solar has happened because an incredible benefit of total cost of ownership. But factor in everything. Do the honest thing around systems calculations, right? You have to permit these things. You have to deal with AHJs on getting approval. You can't have a fire. You can't be visiting it every 2 weeks for maintenance reasons. You have to be able to, be useful in a negative 10 degrees C environment and not brick the thing. You gotta be useful when it's, 40 plus C hot in the afternoon somewhere. Because if you destroy the equipment in those situations, or if you have to run someone out to the remote place to go fix it, you've blown up the economics of it and you lose the access. Right. Access is not just CapEx, it's not just OpEx, it's total cost of ownership. And that means you have to be honest. Do we need temperature control systems here? Do we need insanely complex BMS, battery management systems, so that it doesn't go haywire and hurt somebody? Do we need special protections, right? When you think about energy storage, you're talking about a pretty high energy density for a mineral. And we're doing quite artificial things that don't happen in nature naturally when you use these elements, minerals, in this application.
Right.
And for, frankly, ever since now, zinc has been characterized as an amazing energy carrier, but it has a characteristic, if you don't do something special about it, to short itself out. So really abundant, mineral is everywhere, very low cost, totally accessible, no conflict in the supply chain, yada, yada, yada. But if it dies on one use, you'd say, not that useful. So this is, I think, the honesty that we need to bring to the energy storage conversation, and to say the world started out in a big way towards NMC batteries, right? They were the rage. Oh, geez, but yeah, you're mining cobalt in the Congo with children. That's not good, right? Okay, so that's not good. And it also has a very, very high potential for fire, and fire not just like poof, but arc fire over extended periods of time that regular fire people have a lot of challenge putting out. And it also off gases when it's in fire, a vapor that's toxic. So not a good result. Then all of a sudden the world invents, China predominantly, LFP, lithium iron phosphate. Okay, lower potential for fire, that's great. Lower cost, okay, that's good. Here's a little problem with that. Lithium is still controlled by one country, one source. That's a bit of a problem. But secondarily, this stuff doesn't recycle. There's no economic reason why someone would want to recycle this, because you have to put extraordinary energy into an LFP cell or pack to break it apart, and also add a bunch of pretty harsh chemicals. That's all cost. And now what do you get? You get not battery level lithium out of it. You get iron and phosphorus. Hooray! All worth basically nothing. So no one is going to invest in recycling lithium iron phosphate. What does the world get out of that? Landfill, poisoned water. Hooray, we're back to the fossil economy again. Externalize your exhaust, externalize your negative outcomes. That's not where we're going. That's not where we can go.
So solutions?
Well, Mike, this is a solution right here.
Kerim, when we first talked, we kind of said, look, the US Navy was looking at something which was an alternative, right? So they've been playing around with lead acid batteries, and playing around is the wrong term. They've actually, a lead acid battery, very robust, right? It's a legacy battery, been around for about 150 years, but it just takes up too much room. And it's heavy.
Yeah.
And so the Navy, as they're moving toward, you know, a more digital Navy, needs the room. And you can't just, you know, build more room aboard a submarine, right? Or a ship. So they said, listen, you know, we've got lots of computers, we got needs for backup, we have power and so on, and we need something that's better. And they started taking a look at lithium. Why not? Well, they had a bad experience with a submarine, you know, and Boeing had a bad experience with their 787. And somebody, and this is kind of a perfect example to what John was saying, is they took a look at the requirements of the cell and they said, look at all that fantastic energy in that little tiny space. That means it's really going to be lighter, right?
Mm-hmm.
Well, like I said, the Navy lost the sub because guess what? Lithium batteries don't really do well with salt water, right? And if you don't manufacture them perfectly, take Samsung, for example, you know, you burn not just a foam, but the car or whatever that's in it. And the Navy lost, you know, a submarine. Now, this wasn't a big submarine, by the way. It was one, it was a smaller submarine. But the fact is, you know, you can't have that kind of thing happen.
Right.
The same thing happened with Boeing. You know, engineering said, we've got this fantastic aircraft, 787, all composite aircraft. We want to have the most lightweight we can of all the systems. So they put a lithium ion battery in there. A fire resulted, and I don't know if I told you this last time, but my brother-in-law and his wife were to be on that airplane.
Wow.
They were supposed to be on that airplane, so it's somewhat personal. What Boeing discovered, number one, is the fire burned so hot that it completely destroyed the battery, so no forensics could take place. They couldn't even determine what the cause of the fire was.
Wow.
From an engineering point of view, that's bad, right?
Yeah.
Because now you've got an open question. What caused that? And if I don't know what caused it, I don't know how to fix it, right?
Right.
But Boeing's fix then was they said, listen, we can't go back and put in all, well, they could have put in a different type of battery chemistry, but they were already committed to doing that. So they built essentially an iron shroud, a stainless steel shroud around this battery. And then to put that battery in there, two things had to happen. Number one, they had to put a really cool access panel on it because then, you know, the connector came out of the battery and plugged into the wall, and then they had another one plug into it. So now you've got a complexity in just your installation. And then came the question is, well, what happens if the battery does catch on fire? And even though it's in this really cool stainless steel shroud, what's going to happen with it? So now they had to vent the gases, which meant you had to vent it overboard. Well, you just can't drill holes through composite materials, right? And just put a hole in there. No, you've got to design the structure to absorb both the structural load, but also the high temperatures. And you got to put in the system so that, you know, the thing can be vented without disturbing the aircraft flow. That installation costs them over something like $400,000 per aircraft to retrofit it with this fancy new shroud battery combination. And guess what? The total installation weight. So here was this battery, which was supposed to have a specific energy at the cell level of around something like around 120 or something like that watt hours per kilogram. But by the time you put all the equipment around there, it was 25 watt hours per kilogram. They could have put a lead acid battery in there, and it would have been better, right?
Yeah. Yeah.
That's what John is talking about in terms of you have to look at the total system's impact.
Right.
So,
but to be clear, Kerim, Enzinc does have a solution that unlocks zinc as a mineral to be used for superior batteries and energy storage, and it can be in residential applications paired with solar. It can be in commercial installations, industrial, and it can be also used in mobility applications. But they're not alone. Okay.
Yep.
There are other companies using other minerals. There are other mechanical solutions that are interesting, but we just, I think, need to break this.
Right.
This
and that was going to be the point.
Yeah.
Is that, if you take a look, you know, what the Navy was looking at was for a safer alternative. And so they started looking at it, and we're the guys who teamed with them, you know, to help commercialize it. And it turns out that the same thing that the Navy's looking at in terms of a system solution for their ships and submarines and aircraft, that should be used for this new energy economy. And that's kind of what, John and I are trying to put there on the table, which is when you're looking at an energy
safer,
storage,
lighter, cheaper than lead acid and lithium, essentially.
Right. But you can't just look at it at the cell level, which is what everybody's kind of, doing. They're saying, look at the awesome power of energy in that one little cell. And you go, fantastic. But just like Boeing, who said, look at all the energy that's a cell, that's going to be lightweight. And then it bit them. And they said, no, by the time you look at the total installation of what's required from not only just mining it and processing it and using it and then disposing of it, what is the right solution for that total? In fact, we kind of use the term, you need to have an energy storage approach that matches the ethos of the industry you're trying to support.
Sustainability.
Right. And so if you're looking for sustainability and you're looking for it, not only in the manufacturing, but like I said, in the use by society, all through society, then you've got to come up with a solution that's going to fit that requirement. And so what we're saying is, yes, at the cell level, the zinc battery may not be as good as, say, a lithium battery, like the NMC battery that's used in my car. But once again, using the Boeing example, if I take an electric vehicle that only has to go less than 200-300 kilometers, if I put it into using an NMC battery, I need thermal management. That adds weight, right? So that watt hours per kilogram starts to drop. I need a very sophisticated battery management system and all the sensors. Added weight drops again. Armor to protect the battery, right? Drops again.
Which most EVs have today, I assume.
Exactly. And so when people say, look, the NMC battery has a specific energy of around 220 to 240 watt hours per kilogram. By the time you put it in the car, it's now down to around 130 watt hours per kilogram. Right?
So, I mean, this is kind of like the Microsoft OS versus Apple OS problem of the, because lithium seems like the Microsoft OS, which is already taken off.
Yes.
How are you going to stop that?
It turns out though, if what
even though it's substandard.
Right. But the solution thing is, if you actually now have to look at the total system solution and say, awesome, well, what are you going to do with that battery when you're finished with it? And as John said, if you can't economically recycle it, what does that mean? So as we move toward this renewable energy economy, the total cost, right, of all the ancillary costs and stuff like that, someone's going to have to bear those. And I don't think that's going to be swept under the rug for long. Governments and people are just not going to accept
consciousness about this problem, it sounds like.
Well, it's there. I mean, it already is there. We're hearing from major corporates and the largest waste manager in the world that they have looked very carefully at lithium iron phosphate, LFP recycling, and they're deadly afraid that they're going to have to deal with their big corporate customers, take all of our waste, and they're going to get stuck with it. And that's not good for them because their corporate ethos is around sustainability.
So, I mean, curious question I have is Tesla bound by this lithium battery supply chain? Can they eventually switch easily to, I'm saying Tesla, but it really applies to any EV car.
I think that, but Mike, I think we'll agree that Tesla is catering to the 1%.
Right.
And they don't plan, I don't think, to cater to anyone but that for a very long time. And, quite honestly, it's a great business for them to be in. I'm not going to argue that.
Well, it's kind of like the iPhone a little bit.
But we're talking about the democracy of energy. You need to have access. And so it has to be low cost, not only CapEx, but OpEx too. When you look at the total cost, let's just look at emissions for a moment. When you compare lithium to manufacturing an Enzinc inside battery, you're talking a 20x reduction end to end in emissions, 20x. Now, today that's not monetized, but eventually we're going to care enough about the quality of our air and the health of our ecosystem because it's threatening humanity. Eventually we're going to say, holy cow, that's important. Now, the other thing I would suggest is be careful about how are you going to manufacture 1 million of some of these impossible materials. It's like, oh yeah, all we need is 99.9.999% dry air so that this thing doesn't burst into flames. You know, let's talk about solid metal batteries. Oh, they're so fantastic. Yeah. Okay, that's a fire.
Right.
And you look at some of the high flyers in this like exotic lithium space, manufacture those at any scale that we care about. Whoa, never been done on Earth before.
Kerim, how long did it take for thin film solar to get put in place?
And then die.
Yeah, exactly. That's a good comparison.
So I mean, I just think that the manufacturing challenges that people are going to have around some of the solid state batteries and stuff are going to be some of the same challenges that thin film solar faced.
Yep.
Yeah.
Well, listen, I think that taking the systems approach and weeding through the, let's not say deceptive, because that would imply some things that we don't want to say, but people like to be very selective about the information they talk about for their solution.
Right.
I think that bringing systems level honesty to the energy storage conversation is critical to us actually solving this challenge. Not just like making a good little company that pops and then everyone goes, hee, and we SPAC it and put the risk on the public and yada, yada. Like if we are genuinely interested in deep penetration of solar and wind and electrifying all of our mobility in our homes, we must have superior energy storage that actually works and performs the way we hope it will. That means a system approach is the only way.
Makes sense.